All right, so we got the quiz on 27 today. Any questions?
Number 82.
Ah, the infinitely long network. So we're out there at the edge. And again, why do I press my number? And each capacitor is 1 microfarad. I haven't forgotten you. All right. So this bit right here, let's assume has some equivalent capacitor. Just call it CEQ1. At that point, we would have a series of these two right here plus whatever this equivalent capacitance is. And so 1 over the actual equivalent capacitance is going to be 1 over 1 plus 1 over the other one plus 1 over what I'm calling CEQ1. Oh, sorry. Started going about it one way, and then I thought, oh, wait a second. Yeah, this,
I use the CEQ1.
wait, hold on just a second. I have done it that way. I remember there's the way I usually go about this problem, and then there's my recollection of a slicker way of doing it. Because we are adding one of those. Okay, I'm back. All right. So whatever this is from here, from there on, I'm just calling it the equivalent capacitance 1. So Mario, you had a question?
The way you had it in the book, it was the part 3 had an equivalent capacitance because they're in series, and then they would be in parallel with the other one right here. So then you can add those. So that C1 would be added to the equivalent capacitance of the 3 in series. The final 3.
Yeah, I'm slowly getting there. All right, so the equivalent capacitance of the whole thing would be the equivalent capacitance of this part plus that. But because this is infinitely long, that the equivalent capacitance of this is basically an infinite series starting with, I guess I can start here, starting with that. I guess that's the equivalent capacitance there, sorry about that, which goes with what Mario was saying. So let's start again. And I'll just edit this out like it never happened. It came in too soon. There we go. So I have that bit right there, which has some equivalent capacitance, which I'm going to call CEQ1 for right now. Textbook immediately jumps into calling it CEQ. So this has some value here. This is in parallel with that. And so if I found, so this would have the equivalent capacitance of just CEQ1 plus C, because each of these has some equivalent capacitance. And so then I have this series here of this one, this, and that. So my equivalent capacitance for the whole thing is going to be 1 over C plus 1 over C plus 1 over C plus what I'm calling CEQ1. Now, this bit right here is an infinite series of pretty much the same thing as this. We're just adding, if we add one of these units here to an infinite string, we still have an infinite string. So, therefore, since it's converging from physics point of view, we can just go ahead and say that, well, the equivalent capacitance of the whole thing is basically equal to the same thing minus one of these units. Minus, if I took that out and just moved my probes to here, I should get pretty much the exact same reading. So making the, I guess they are converging on the same point, that CEQ and CEQ1 are the same thing. So 1 over the equivalent capacitance is equal to 2 over the capacitance plus 1 over C plus CEQ. That this and this are equal to each other. So if we get a common denominator, this becomes 2 times C plus CEQ plus C over C times CEQ. That's C plus CEQ. Is that the simplest way? Yeah, we're here now. Cross multiply. I guess I could have just multiplied by the LCD. So what I end up with is C squared plus C CEQ. And just for the sake of ease, because I got a lot of C's here, what I'm going to do is I'm just going to let CEQ just be the letter X, just because I don't feel like writing it. So C squared times CX equals 2C plus 2X plus C times X. Because again, given my shorthand notation, that's X right there. And this is X right here. So I have C squared plus CX is equal to 2CX plus 2X squared plus CX, so we make that 3. All right, questions to here, because at this point it's just a math problem. Since we want to find the equivalent capacitance, we're solving for x. I have a quadratic, so let's set it up for a quadratic. I have 2x squared. Getting everything over on this side. Plus 2cx plus c squared equals 0. So x equals negative 2. Well, c is 1 microfarad, so c equals 1, plus or minus the square root of 4 minus 4 times 2, 4 squared. No, wait a second.
Yeah.
I lost something here. Minus, I have 2x squared that I,
It's minus c squared.
Depends on which way you move it.
I moved everything over, I moved this over that way. So minus c squared, there we go. And then whatever that ends up being.
Which value would you take?
Right. As in, would I accept that as an answer?
No, it's gonna get two values, right?
So we'll have a positive value and a negative value. You should never have a negative equivalent capacitance. So take the positive one. That's about 1.3 something.
0.360.
Because we're subtracting 2, not adding 2 there. So 366. Microfarads. My traditional approach for this is basically start with one and then add another one, then add another one, and look for the pattern that emerges. And so that's generally where my mind goes immediately for this type problem. It's much more cumbersome. So what was the specific thing about this problem that messed you up?
Well, I just didn't understand how the textbook set
Just,
it up.
okay. Are you good now?
Yeah.
All right. Any other questions about this? No other questions?
Number 88.
Parallel capacitor, square plate, site S is 2.5, all right. So we've got kappa, some distance y, positive q, negative q. All right. Parallel plate capacitor has square plates, S 2.5 centimeters. So the plate is 0.025 times 0.025 meters times meters. 0.0625 square meters. Q is 4 microcoulombs. We have permittivity of 6.5. Sorry, dielectric constant, 6.5. And it goes in 1 centimeter. effective capacitance of this capacitor. All right, so basically, as I said, you're treating it as in parallel. I've got two like this. Did they give us a gap between them? Okay. I know the capacitance is equal to kappa epsilon sub naught A over D. So if I treat this as capacitor 1 and capacitor 2, I know my equivalent capacitance is capacitor 1 plus capacitor 2, because they're in parallel. And so the first one has a kappa of close enough to 1. I don't know if it's officially a vacuum or if it's just air, but close enough to 1. Times epsilon sub naught times my area of that part of the plate, the part that doesn't have anything in between. So I know it is 2.5 centimeters depth, and the height here is 1.5 centimeters, because they tell me that the dielectric goes in 1 centimeter. So my area is 0.025 times 0.015, divided by the distance between them, 0.0025, plus, very similar to what we just had, except we now have a dielectric in between, and the height's a little bit different. So this becomes 6.5 times 8.85 times 10 to the negative 12 times 0.025 times 0.01 divided by 0.0025. So that's the individual capacitances. And that's the main part that I wanted you to get out of it. And then B is energy stored. That's the plug and chug into the formula. But we'll just pause here. Questions on this part? Didn't really derive the formula for the energy of capacitance, but 1/2 U squared over C. One of those ones they don't memorize. So they had 7.0 picofarads. To the negative 12 farads. I'm assuming it comes out to that. Okay.
I have a question.
Yes.
On the explanation, for the capacitor that had, the dielectric constant, you had the area as 0.025 times 0.01, and then for the second capacitor, without the constant, the area, one of the sides, you have 0.025 minus 0.01.
So in the solution?
Yeah. So would that make a difference in the answer?
No, what they did is they did 0.025, actually they did this one first, 0.025 times, I think it's 0.01 is, yeah, times 1 times 10 to the negative 2, 0.01. And then over here they did 0.025 times 0.025 minus 0.1.
Mhm.
0.01.
Okay, I see what you did.
And I went ahead and did the math in my head.
Okay.
So that's the difference there. I think that addresses what you were talking about.
It does.
Okay. And then C see magnitude and direction of force exerted on the dielectric by the plates of the capacitor. Oh, they're using the formula there. Yeah, I'm not gonna worry about that right now. All right. Part A was the big part that I cared about. Other questions?
Why did you use capacitance is equal to K epsilon to naught A? Why do you use capacitance is equal to K epsilon to naught over times A over D instead of the capacitance is equal to just epsilon to naught A over D?
The kappa is if you've got a dielectric in between. Well, technically, you could have a kappa there regardless, but if there's no dielectric, kappa is equal to 1. But in this particular problem, I have part with a dielectric and part without. So I knew a dielectric was coming into it, so kappa, may as well put it in there.
Okay.
Just kappa is equal to 1 for the top part and 6.5 for the bottom part.
Okay.
All right, we got the flash quiz first. Usually I start out with that. And I have them here. Any questions?
I know this is in the syllabus. How many tests are
There'll be 3 test grades. No, sorry, 4 test grades. So you've had one, I'll hand that back tonight. And then you'll have what I call test 1B. That multiple choice thing you did the very first day, you'll do that again.
Okay, so is that test 1B?
The test 1B is going to be chapters 27, 28, 29.
Okay.
And then the last test will be basically everything magnetism onwards.
So we're getting test 1A back tonight?
Yes. I assume that is being met with great joy.
Anticipation.
Mm-hmm. All right, it is recording. All right. So let's talk about circuit analysis. That's what we're doing tonight. And at some point, just to give you a peek into great anticipation, it is going to get potentially tedious. Because there's a variety of math backgrounds here, and so I do need to go over some stuff that some of you will look at and go, everybody in here knows this, and I will assure you, not everyone does. Unless this group is different than any other 252 group I've taught. Well, we'll start out, before we get to the really tedious piece of it, so let's talk a little bit about, well, a couple things here. Let's make this 4 volts, 3 ohms, epsilon 1, R1, epsilon 2. Let's do a different number here. 5 volts. All right, so the epsilon comes from the expression of EMF. Or sometimes written EMF. When they were trying to figure out why batteries worked or coming up with a notation, they thought, well, there's some force, there's a force that is causing the electrons to move, or the current to move, probably at that point. And so they decided to get clever and call it the electromotive force. Which they then abbreviated to EMF. Then they realized that it's not actually a force that they were talking about, it's actually voltage. So we still use the term EMF, because they originally were thinking it was a force instead of a potential difference. So at this point, even though historically it comes from electromotive force, EMF officially does not really stand for anything. So it's just EMF. And it's an ideal voltage from a power supply. Now, I will tend to use EMF and voltage interchangeably. The purists out there will object to that, but just warning you. So that's why there's an epsilon there, and that's typically the symbol for EMF. So I got a 4-volt battery, and I got a 5-volt battery here. So we're just going to go through a tedious way of looking at it. We've done something very similar to this. I don't think we did the 2 batteries before, but I'm going to start here. We have Kirchhoff's loop rule or voltage rule, the fact that I should be able to go around, and my total voltage should be 0 in the end. So I have the voltage across EMF 1, plus the voltage across resistor 1, plus the voltage across EMF 2, plus the voltage across resistor 2 should be 0. So I add them all up. So I'm going to start here, and basically I went around, and so I know that I'm going to gain voltage going across here. Actually, I'm going clockwise. Yep, that's clockwise. How do I know I'm going to gain?
Go from negative to positive, so from low to high.
Yep, that's my low side, and that's my high side. So I'm going to gain there, so that's 4 volts. And I know it's volts, I'm just not going to bother writing units. When I go across a resistor, well, I know my current is going to be flowing this way, because current flows out of the positive side. The electrons flow out of the negative side, but the current flows out of the positive side. And so if I go across a resistor with the current, I'm losing potential. So minus my current times my resistance. This is Kirchhoff's, this is Ohm's law, which we derived last time. Plus, I'm gaining going across the other one, then minus 6I. Then just to be consistent, 3I, doesn't really matter if you write it I3 or 3I, equals 0. And it's a relatively simple algebra problem, or pre-algebra. 9 minus 9I equals 0. And so mathematically, I is equal to 1. But we are better than that. What is the real answer? Thank you. Yes. 1 ampere. So in a simple circuit like this, I have 2 batteries helping each other. So what happens if I flip a battery around? So we'll use the magic of the board. And I'm going to take that and flip it around. What changes? This first line is still true. I should still end up back at 0 when I get to the beginning. What changes in the second line?
Would there be a change in the direction of the current?
How does that affect the second line?
Would you be losing the 5 volts from that power supply?
You would be. Now, getting back to Precious's comment, let's address that in just a moment. That's minus 5.
Would you add the resistor then?
Excuse me?
Would you add the part from the resistor?
Nope. And that's going to come back to what Precious was asking about. And so now my current is negative 1/9 amperes. The negative means that, oh, the current is going in the other direction, as you were saying and as you were potentially speculating. But we decided, sort of a royal we there, I went ahead and said, well, let's just make I going in that direction based upon what we originally had. And we ended up saying, oh, we got a negative, that means current's going the other way. So my current going across the 3 ohm resistor here, across the 3 ohm resistor, is negative 1 ampere to the right, or positive 1 ampere to the left. The negative just means the other direction.
So if instead you chose current to go in that direction, it will be positive?
All right, so let's play around with that a little bit. Questions on this before I start flipping stuff around? Now I'm going to say that I is going this way. That still holds true. Now the direction I go around, let's just go the same way we did before. We'll just start there and work our way around. So I go across this one, I gain 4 volts because I'm still going from the low to the high. I'm going across this resistor now. Now I'm going upstream. If you think about it, a river runs downhill. If you're going against it, that means you're moving uphill. You're gaining potential energy in that analogy there, or gaining potential in this one. So this is plus 3I minus 5. The current is going to the right across this one, but my loop here is going to the left. I'm going against the current. Plus 6I equals 0. So negative 1 plus 9I equals 0, or I equals 1/9 amperes. Which means that the current flowing across this one right here is, so the current across resistor 1 is 1/9 amperes to the left, or negative 1/9 amperes to the right. But that's exactly what we did before. So the direction I choose my current to be in the beginning is completely irrelevant to what my final answer is going to be. You pick a direction and you live with it. Matter of fact, the direction I take my loop here doesn't matter. I'm going to get the exact same answer. Now it might be plus 1/9 or minus 1/9, depending upon the way I have to find things, but it's still going to ultimately end up with the same current in the exact same direction. When we get to more complex drawings, this will become a relief, because it's less decision on your part. You just pick one and live with it and go with the math with that. Okay, questions to hear? Now for you future electrical engineers or people who dabble with that a little bit. I have no idea why you would design a circuit with two batteries fighting each other like this, but we will do a number of, it's a classic academic thing. We give you problems that have nothing to do with real life, other than the fact that the process that we're going to go through. I tutored a young lady years ago who was complaining about math, and she said, why on earth would anybody have a garden that was in the shape of a parabola? Because they're math teachers, they wanted to play around with that. All right. This is something that we will definitely delve into more at some point tonight. And actually, I want to. I have a capacitor and I have a resistor. Let's make this the high side and the low side. So I'm going to start out with a charged capacitor. And what I want is an equation for the current. So first off, the capacitor is already charged to its maximum. Which way will the current flow? Okay, I've got a counter here. You also said counterclockwise?
Yeah.
You were a little less sure. All right, so you're saying counterclockwise, you're saying the current's going to flow this way. Why?
I'm assuming that electrons are flowing from the negative side, away from the negative side.
So the electrons are going this way?
Then current flows in the opposite direction.
Yeah, current flows from high potential to low potential. Let's do our Kirchhoff loop. Doesn't matter where you start. Personally, I always like the first thing I do to be positive for whatever reason. So I'm going to start here, and I'm going to go in the direction of current. So I have some current flow here, I. I'm going across my capacitor. So I have some potential across my capacitor plus the potential across the resistor. Sorry, potential difference, not potential. Potential difference across the capacitor plus across the resistor is 0. At some point, we will quickly abandon this first step and jump straight into the second step. I know that capacitance is equal to charge divided by the voltage. And so therefore, my voltage is charge divided by capacitance. I'm going across my capacitor here. I'm going from the negative to the positive plate. So am I going to have a gain or a loss of potential? What as I go in my loop? So this will be Q. And I'll put a little C there because we do need to differentiate the currents. This is the charge on the capacitor divided by capacitance. And then I'm going in the direction of my defined current here across my resistor. So it's minus I times R is equal to 0. Now I have two variables here. I have the current that's on the capacitor, I have the charge that's on the capacitor, and I have a current flowing across the resistor. Presumably I know what the resistance and capacitance are. So I have to get them in terms of a common variable in order to solve it. Well, what's current? Saw some wheels turning. Someone's just going to board it out. Looks like I can do the first part here.
the charge over time?
We can do a little bit better than that. In essence, yes, but we're doing calculus here, so what's the calculus version?
Yeah.
Now let's be careful here. This is the charge that's going across the resistor. These two Q's are not the same. They're related, but they are not the same. So let's actually relate them. The charge that's going across the resistor is the charge that has left the capacitor. So the rate at which charge is lost here is equal to the rate at which charge is gained here. In other words, dQr dt is negative dQc dt. Whatever the resistor gains is matched by whatever the capacitor loses. And so my equation here becomes QC over C plus dQc dt R equal to 0. I have a first order differential equation. Separate them. So let's do negative QC over C equals R dQc dt. Just basically brought QC over to the other side and flip the order in which I'm writing the equation. Again, negative 1 over RC is equal to dQc dt. Oops, I lost my Q. And then let's bring all the Q's on one side and the non-Q's on the other. So I get negative 1 over RC dt is equal to dQc over QC. Since ultimately I'm looking for an equation for current, what I actually can do in the interim is come up with an equation for the charge on the capacitor. So let's integrate both sides. R and C are constants for a particular problem. I guess if you want to make it complicated, you put in the temperature dependence of the resistor, and the temperature will change as you run the circuit, but we will ignore that. From 0 to some time, from Q max to some charge. And so I have negative 1 over RC times time equals, well, the natural log of Q sub C from Q max to Q. So negative 1 over RC times time is equal to the natural log of Q minus the natural log of Q max. And let me make sure I didn't mess with a minus sign here. I feel like I did. As time increases, that's a positive number, but the Q C is getting smaller. Oh, no, we're good. All right. We're trying to solve for Q. We're trying to get that equation there. And so let's add this over to the other side. So I have the natural log of Q max minus 1 over RCT times time is equal to the natural log of Q. Not particularly a nice form because we want Q equal to something, and so let's exploit our E there, or our natural log, and so Q is equal to E, the natural log of Q max, minus 1 over RCT, which is E, which ultimately is just Q max, times E to the negative 1 over RCT. So when time is 0, we can double check ourselves. When time is 0, this whole term here equals 1. And so my charge is equal to the maximum charge. It's whatever I started with on the capacitor. So that makes sense. As time goes to infinity, I have e to the negative infinity, so this whole term becomes incredibly tiny. And so the charge of capacitors becomes incredibly tiny. That works.
E to the what?
Negative RC times T. So let's see. So Q is equal to my Q max, e to the negative 1 over RC times time. Sometimes written just as legitimately, Q max, e to the negative T over RC. So if I plotted that, Q versus time, and I have some maximum here, this is Q max. It's a negative exponential approaching 0. And that's basically what's happening to the charge. You get a lot of charge lost quickly, and then the rate at which charge is lost gets, the rate lessens, which makes sense because it's the positive charges or it's the charge of the other things on the plate that are still forcing the electrons off. Right, that one again. The electrons hate each other. You complete the circuit, the electrons are forcing the other ones off. As you lose charge, there's less of a force pushing these electrons off. Also note, we haven't actually answered the question yet of what is the current. So how do I find the current?
Can you just divide both sides by time?
More sophisticated than that. I have time in an exponent here. It's not going to be particularly easy to divide by that. How do I find current? I know it was like 3 minutes ago, but hoping you remember. Really.
Respective time.
Pardon?
Would you take the derivative with respect to time?
Yeah. So this is the charge that's on the capacitor. So dQc dt would be negative Q max over RC e to the negative T over RC. That is the rate at which it is being lost off the capacitor. So the current, which is actually what's going across the resistor, the current would be the negative of that, Q max over RC, e to the negative T over RC. a bit of vocabulary. RC is known as the time constant. There are various time constants. This is one of them, so I guess I should change that. This is known as a time constant. And it's specific to a particular problem. So when time is equal to R times C, then what I have here is my current, I guess we can do it in terms of current, is Q max over RC, e to the negative 1. Which is that 0.29?
0.367.
367. So you can express things in terms of time constant. After one time constant has gone by, we are at just under 37% of what we originally started with. After two time constants, will be even less, and so you can express things in terms of time constant instead of specifically time. There are just times in which, there are occasions in which that has an advantage. Questions here? All right. Let's make it more complex. I guess I should start erasing on this side. I think I've done enough preliminary stuff, so let's just jump straight to, a test level problem. And I will guarantee you, the last question on test 1B will be something similar to what I'm about to do. I think that's pretty much the design I always see. Resistors pretty much always in the same place. The batteries could be flipped upside down, and the numbers will vary. And let's see if I actually have an easy one here where you actually get integers as answers. Otherwise, I will just make up numbers and we won't have integers. All right, I would just make up numbers. At some point, I might ask you if you want the problem to have integers as answers on the test. The advantage of, if you know ahead of time they're going to be integers, then if you get integers as your answers, you should feel pretty good that you probably did something right. The disadvantage is if you know there's integers, the answers will be integers on the test, and you don't get integers, then you could probably spend the next hour trying to figure out where you have a minus sign in the wrong spot. Turns out how much you want to torture yourself. So let's make this 1 volt, 3 volts, and 5 volts. And usually a volt starts with the letter V, so let's do that one. And we'll make this 2 ohms, 4 ohms, 6 ohms, and 7 ohms. There's also a master set problem very similar to this. And this is a 1, not an I. The question is, what is the current flowing through each of the wires? I have 3 wires here. These are my junctions. I have this wire to the left, I have the wire in the middle, and I have the wire to the right. There are two major techniques, and so I'm going to take you through the process, the two different methods of setting it up, and then three of many math methods to solve it. I'm not going to specify which one that you would pick. Sometimes there'll be classes that are evenly mixed between the different methods, and sometimes the classes will sort of gel around one particular method. I've had students ask me, why don't you just teach us one? And that's because not everyone's mind works the same. And so I'm going to teach you a smattering of things, and you pick the one that you like. So, technique number one. The one current per wire. I have three wires here, so I'm going to have three different currents. First thing I do is I decide, all right, what is the direction of the current flowing through the left wire? It really does not matter which way you pick. Some students will always pick the same direction every single time, and that's fine. Some students will mix it up. So I'm just going to say that from here all the way to here is the current, and I have it going clockwise, and I'm going to label that current A. The reason I'm not choosing I sub 1 or I sub 2 is the fact that I'm going to be writing so many subscripts if I label it I1, I2, I3, that I increase the chances of making a careless error. And there are loads of places to make careless errors when doing this. In the middle, I'm just going to say down. That's current B. And then on the right-hand side, I'm going to make this one go counterclockwise, and that is current C. When doing this, current is going from junction to junction. Some students get overzealous and they draw, the current's flowing the entire loop. But that's a completely different process, and it can lead to some great confusion later. All right, so I've established my currents. Now we do my voltage loops. I have three unknowns here. One of my equations, try that one again. I have three unknowns. How many equations do I need? Absolutely. One of my equations employs Kirchhoff's junction rule, or current rule. I don't care which junction you pick. I usually pick the top one for, the usual scars. Current flows in is equal to the current flowing out. Well, my current flowing in is C. My current flowing out is, C and A are flowing in, and what's flowing out is B. There's one of my equations right there. If I had all three of them going into it, so if I flip B around, then I'd have A plus B plus C equals 0. And that's fine. I know one of them is going to be negative. At least one will be negative. It's okay. Now I have a choice of three, what I'll call Eigen Equations. As long as I end up back in the same spot, I'm going to do the voltage loops now. I'm going to start in some spot, I have to end up back in the same spot. I have three basic ones I can choose. I have the left loop, I have the right loop, or I have the entire loop. Now I was going to say you have a choice of three, and then I stopped myself because you actually have an infinite number, because I could start here and do a figure 8. It's a waste of time, but I could do a figure 8, or I could start here, do a couple of loops around this side, and then come back. So please don't. Just know that you have the satisfaction of that you could if you needed to. But you'd ultimately end up with a whole bunch of stuff that would just cancel out immediately. So we have left, right, and the whole. So what I'm going to do is I'm going to do all three equations. However, we need two of them. So, and then I'll explain why you don't use all three, why you have to use this one. All right, so we'll call this my left the left loop. I start here, and again, I want my first number to be positive, and so I'm going to start here, and I'm going to go that way. One. We're off to a roll. We're off to a start. I'm going across the 2 ohm resistor in the direction of current. Minus 2A. Now heading down the middle, because I'm doing the left loop here. Heading down the middle. What's my next term?
Minus
6B. What's my next term? Ooh, you skipped one.
Minus 6A.
You skipped
Plus 3.
Oh, right, yeah.
plus or minus 3. All right, then we head around to the bottom. Equals 0, because I'm back to where I started. Now, the 7 ohm resistor and the 2 ohm resistor are technically in series. Any current flowing across here has to flow across there. Some students will just go ahead and add them straight up. It doesn't matter if you do or not. I've got my minus 2A here, my minus 7A here. I'm going to add them in the next stage if I don't do it at the start. All right, my right loop. Let's start here and go that way. What is this one going to be?
Times 4C, or C. Minus 6B plus 3.
Because we end up back where we started. And then for the whole, let's just start here and go clockwise.
Sorry, where are we starting?
Sorry,
Where are we starting?
there. I'm going clockwise. When you said where, I thought you said 1, so I wrote down 1, which is the right start.
Minus 2A. Minus 4C. Or do we go in the middle?
No, the 4 ohm resistor is the right one.
Okay.
It would be plus 4.
Plus 4, because we're going against current. Plus 4C.
Minus 5.
Yep.
Minus 7A.
Now, some students get into the habit of not writing equals 0. Please write equals 0.
Plus 7A?
No, minus 7A, because I said current was flowing this way across the 7 ohm resistor, so my loop is going with the current. We're going to solve this 6 different ways, so if we make a mistake, we'll find it. But we'll at least know we have a mistake. All right, so I've got my equations here. I have 4 equations. If I use just these 3 right here, let's just see what happens. So what I'm going to do, so what I'm about to do is not going to work, just so you know. I'm going to take these 2 equations, I'm going to take this equation here, and I'm going to subtract this equation. So L minus R. So I have 1 minus 2A minus 7A minus 6B plus 3, that's that equation there. Subtracting the other one, so that's minus 5 plus 4C plus 6B minus 3 equals 0. Take a moment to either find my mistake or convince yourself that I did not make one. Apparently my handwriting just got worse, so let me know if you can't read what I'm writing.
Would it be
I subtracted the whole thing. So all the signs flipped, so it should be -5 plus 4 plus 6
Okay.
minus 3. People generally convinced that I did not make a mistake, or you're still wondering if I have.
Does it have something to do with one of them being in series and the other in parallel?
No, that's not the issue. Just in terms of just straight up math, not worrying about the underlying why you shouldn't do this. All right, so let's simplify this. Well, I got a -6b and a 6b right there, and then a +3 and a -3 right there. So I end up with 1 minus 5, which is -4. And I tend to like to check them off just to make sure I don't lose something. Minus 9a plus 4c equals 0. I think I've done that correctly. So I took the first two equations, combined them, and I got this. My third equation, if I now want to combine with my third equation in order to solve it, well, let's see what we have here. Let's just simplify this. I've got 1 minus 5, which is -4. I got -2a minus 7a, which is minus 9a, and then plus 4c equals 0. You can only solve three equations, three unknowns, if the three equations are independent. These three equations are not independent of each other. I can create the third one from two of them. This is why you should not use these three. You'll use two of these and this to solve. If you did this way, what you should end up with is 0 equals 0, which should give you some satisfaction. However, it doesn't get you closer to the solution. Still remember one student, she sat back there. She tried the three equation bit, and she had a minus sign in the wrong spot somewhere in here, and she actually came up with answers. Because one minus sign in the wrong spot, and then they're no longer, they are now independent of each other. All right, so we'll use that equation up here, and which two of these do you want to use? Do you care?
Let's do the left and right.
Left and right, all right. Now solving it. This is the part that will get a little tedious for some of you, and just sort of bear with it. We will get into something potentially new for you, or something just, again, something you've been doing in your sleep for years. So my three equations, I know that B is equal to A plus C, so let's go ahead and make that substitution here. So first technique here is substitution. So we'll call this math technique 1. And so this equation here, I had 4 minus 9a minus 6a plus c is equal to 0. My one down here, I have 8 minus 4c minus 6 a plus c is equal to 0. So first step, get them in terms of two unknowns instead of three. That's why the first equation is rather convenient doing this. Simplifying this, this becomes 4 minus 9a. Let's see if I can get something darker. I guess this one was working. Minus 6a plus minus 6c equals 0. A second equation here, 8 minus 4c minus 6a minus 6c equals 0. Simplifying, I got 4 minus 15a minus 6c equals 0. And then 8 minus 6A minus 10C equals 0. In reality, when I solve problems like this, I sort of mix the techniques. For what I'm doing right now, I'm not going to mix the techniques. I'm going to stick to the purity of the substitution. And so I'm going to solve for either C or A in one of these equations. And so I'm going to do it from this equation here, because I'm going to end up dividing by 10, which I can do in my head. So I have 8 minus 6A is equal to 10C, or C is equal to 0.8 minus 0.6A. I substitute that now into the first equation. And so I have 4 minus 15A minus 6 times 0.8 minus 0.6A equals 0. 4 minus 15A minus 4.8 plus 3.6A equals 0. And I have negative 0.8 equals, so I got from 15 left over, so this is 11.4A. Give me 3 significant figures.
0.2.
0.2 amperes. Unfortunately, I did use A as the variable and A as the unit, so just sort of be aware. This is amperes here, and that's A for my variable. I'm going to write that over here. So A, let's go slightly more formal. Current A is equal to negative 0.0702 amperes. I'm assuming somebody in here has sort of checked my work as I've gone and made sure I have not got a minus sign in the wrong spot. We'll assume not unless somebody corrects me. So C is equal to 0.8 minus 0.6 times that. Like 7.5 something?
0.758.
8? Let's go one more decimal point.
Well, it's 0.7578.
7578? All right. Current C is 0.7578 amperes. And then B, well, we have an equation right there for it. It's just the sum of those two. It's 6, there's a negative there. 2, 6, 7, 6, 8, 7, 6. Question about the excitement that is this problem so far.
That's just a magnitude, right? Did you already take into account the direction of the equation?
Already took the direction into account in the equations. Our A is actually going in the other direction. But B and C are going exactly what we expected because those were positive, but A is going the other way.
So your net current, when you add them up, you would then take those, you would subtract that from your current?
Well, technically, I added that to a negative number.
I see.
Because I have, at that junction there, in reality, I have 0.7578 amperes going in from the left, or sorry, the right, I have coming down 0.6876 amperes going down. And I had A going into it with a negative value, or it's coming out of it with the opposite of that, so coming out 0.0702 amperes. That's what's happening at the top junction. Did I answer your question? Okay. Other questions up to here? All right, here we go. Math technique number 2. Woo! My equations don't change. I mean, we're still living with that. We still have these 3 equations here. That doesn't change. Oh, I guess technically we're not substituting, so I will start from here. Anybody still writing this down? Oop. Simultaneous equations. I don't know, there might be some official math terms for it, but that's what I call it. So simplifying it, I've got B is equal to A plus C. So here I've got 4 minus 9A minus 6B equals 0, and 8 minus 6B minus 4C equals 0. The second equation here, I've got, let's make sure I have it. So I've got my 8 minus 4C minus 6B, I'm good there. And then up there I've got 4 minus 9A minus 6B. These are all even numbers, so I can just divide by 2 just to simplify it down to 4 minus 3B minus 2C. It's optional if you want to do that or not. So divide by 2. I need to get down to 2 variables here. So what I'm going to do is I'm going to get rid of A from this equation right here. So I've got 4 minus 9A minus 6B equals 0. And this equation here, I'm going to, let's see, I could just multiply it by 9 as is. So I get 9A plus 9C is equal to 9B. And then I just add. So I have 4 minus 6B plus 9C is equal to 9B, or 4 minus 15B plus 9C is equal to 0. So you multiply an equation by some constant, which will get you where you can just add up equations and cancel out. I now have this equation and this equation. So what I'm going to do is I'm going to multiply this equation by 5, because I have negative 15b here. So actually, when I multiply by negative 5, so then I'll get positive 15b there. And so I have negative 20 plus 15b plus 10c equals 0. And 4 minus 15b plus 9c equals 0. And so I get negative 16 plus 19c equals 0. And so c is equal to 16/19, which I hope is 0.7578. It's not? All right, so the question is, where is the mistake? How close are we?
0.842.
Yeah, okay, that's not close. All right, so let's just double check here. If that's correct, I'm good with that. here we have 4 minus 9a minus 6b equals 0. That seems good. 8 minus 6b minus 4c equals 0. I divided by 2, so 4, 3, and 2. This equation here, I took that one, and then I multiplied that by 9. Add together, I get 4 minus 6b plus 9c equals 9b. Subtract 9 from both sides, 9b. 6 and 9 is 15, so that seems legitimate. And then multiply that by negative 5, so negative 20, 15, and 10. I am not seeing any mistake that we made here.
Maybe we
Maybe
made
we
a
were
mistake
just
the
like,
Yeah. So this was, you said 0.80,
842.
4, 1? So we're going to press on. Let's assume that this is correct. We'll double check ourselves at the end. I have a value for C here, so I should be able to plug into an equation. This is probably the simplest equation right here. So I have 4 minus 3b. You know what? Let's stick to the purity of the method. So from this equation and this equation, I'm going to multiply this equation by 9 and this equation by 2. So this gives me 36 minus 27b minus 18c equals 0. That one is 8 minus 30b plus 18c equals 0. Add them together. My c's cancel out this time. And so I'm left with 44 minus 57b equals 0. And so b becomes 44/57. Answers. Which is
0.7719.
0.7719. Oops. Equal sign inappropriate there. Or and purity of the method is tedious, so A equals B minus C. And so by this, Windows 702, negative. So we agree on that at least. But we have our values for B and C. Let's see if it checks out in this equation right here. Let's give ourselves a little bit of room. So I have 8 minus 4 times my value for C, which was 16/19, minus 6 times our value for B, which was 44/57. Oh, all right, did come to plus 3. And what does that actually equal? Equals
0.
0. All right. So it's looking like this was the correct one. And I don't want to shock you, but I did write this up correctly here. Negative 0.0702 is equal to negative 0.0702. I know potentially it's rocking your world, but just sort of go with it for now if you don't believe it. questions here before I do the one that is the one most likely, you're least likely to have done before. Bottom line is, questions? How many of you are familiar with Cramer's rule? Determinants. How many of you dealt with determinants before? One. Okay. And a half?
I think I have,
All right, I want to keep these equations here, so I'm going to write them off to the side over here. We have B equals A plus C, and then 4 minus 9A minus 6B equals 0, and then 8 minus 6B minus 4C equals 0. A plus C equals B, and that's, all right, I think those are written correctly. Oh, wait, no. Cramer with a C. And be assured that 20 years ago, I would have done a Seinfeld reference at this point. All right, so let's start out with determinants. So a 2 by 2 determinant is, we'll start out with a 2 by 2. Ultimately, we need to get to a 3 by 3. So a 2 by 2 determinant, if I have 4, 3, 7, and -2. Now, I'm about to go into one specific way of doing determinants. There are other ways of doing it. You actually can start anywhere. However, this is a case where I am going to do it one way. I'm going to start in the upper left-hand corner every single time. So you start in the upper left-hand, so I'm starting in the upper left-hand corner, and I write down the number. I ignored that everything in that row and that column, and I write down what's left over. This is not an absolute value sign. This is a determinant sign, symbol. So I'm going to take the determinant of -2. That's where I start. And then I move to the next one. I come to the 3 here. Now I alternate signs, so that's why I'm putting a minus here. 3. Then I sort of ignore that row and that column. What I'm left with here is a 7. And so the determinant of this 2 by 2 array is, well, the determinant of a single number is just that number. So this is 4 times -2, or -8, minus 3 times 7, which is 21, -29. That is the determinant of this matrix. I guess officially not array, but I will probably continue to say matrix.
Isn't that just basically, it's another way of saying that, like cross product?
For the 2 by 2, it does shorten down to that minus that. That only works with the 2 by 2. I hesitate to use the term cross product just because that has so many other meanings. Or are you doing that you can do cross products with determinants?
You can do cross products with determinants.
Yes, you can. Okay. So some of you have dealt with determinants before? Okay. You were just shy before, or you need a refresher? Okay. That Calc 3?
We just did it not so long ago. It was the beginning of the course.
Ah, okay. Questions on this? Let's do a 3 3 by 3. Start in the upper left-hand corner where I have a 1. I block out that row and that column, and I write down what's left over. 9, negative 2, 7, 5. I then work my way left, or right, as people say today. Alternating signs, so minus 4. I ignore that row and that column, and what I'm left with is 8, negative 2, negative 3, 5. For those who have not done this before, just convince yourself of why those are the numbers written down, or ask why. Plus 6, because again, alternating signs, and then block out that row and column, and I'm left with 8, 9, negative 3, 7. And now I'm back to the 2 by 2, which ultimately ends up being 9 times 5, so this is 1 times 9 times 5, minus 7 times negative 2, which is 1 times 45 plus 14, or 59, minus 4 times 8 times 5, which is 40, minus negative 2 times negative 3, which is 6. So 4 times 36, which is 144. Plus 6 times 8 times 7, which is 56, minus negative 27, which is 6 times 83. I think it's 498.
I think that should give you 421.
The final answer, or
The
no?
final answer.
421. Okay.
Is it 40 minus 6?
Yes, 40 minus 6,
So
because negative 2 times negative 3 is
that's
positive 6.
34.
Ah,
So that middle one should be negative 136.
did you already take that into account when you got the 421?
No, I wasn't going based off of yours, I was doing my own calculation.
Okay, so 421 is still the correct answer? All right. And there was a demonstration of why there are so many places to make a careless error. There's the goal to have everyone in class actually get the last problem on this on the next test 100% right. I've had one class get over 50% getting their 100% right. I want this to be the second class to do it. Daniel.
So, that was gonna be my question. So when you say similar, you basically mean that it's just whenever it's like on the test.
On the test, I would give you this, and then you solve it however you want to.
Yeah, but I mean like probably the same setup, but just different.
Oh, yeah, and the resistors, I think, are pretty much in the same spot. Batteries are in the same place, but the batteries might be flipped over. Yeah, it's gonna be a problem like this, very much like that. But there are so many places for a minus sign to be in the wrong spot, and then there's also you're taking a test, and sometimes your mind's in gear, and sometimes it's not. All right, Cramer's rule. Now that some of it's come back, have you done Cramer's rule before? You have done Cramer's rule.
Isn't it where like A X equals B and A B equals F? Or?
No, not. That description does not ring a bell for me. So I'm going to take my three equations over there, and there's a particular format. I want all the A's lined up, B's lined up, C's lined up, and then the constants over on the other side of the equation. So I'm going to take that first one, and I have A minus B plus C equals 0. To subtract B from both sides, I do it in the order of A, B, C. It doesn't have to be, but I just find that easier. The next equation, I have negative 9A minus 6B equals negative 4. Feel free to multiply through by negative 1 to get rid of the negatives if you want. It will not change how you get the final answer. This one right here, you can divide by 2 if you want, or leave the numbers there. We'll just leave them there for right now. So I have negative 6B minus 4C is equal to negative 8. So I'm going to set up a fraction for all of them. It's going to be one determinant divided by another. The denominator is the same for all three of them. The determinant for the denominator is just the coefficients of A, B, and C. So my first row is 1, negative 1, 1. Second row, negative 9, negative 6, 0. And then 0, negative 6, negative 4. Obviously, we have to do something for the numerator, and we have to somehow bring in the right side of the equal sign into the equation, and this is where we do it. On the right side, since A is my first variable here, I'm going to replace the first column. So I'm going to replace the first column with 0, negative 4, negative 8, and I'm going to write the other two columns exactly as they were before, negative 1, negative 6, negative 6, 1, 0, negative 4. So my denominator, 1 times negative 6, 0, negative 6, negative 4, minus negative 1, negative 9, 0, 0, negative 4, plus 1, negative 9, negative 6, 0, negative 6. I see you're struggling there, Kyle. Do you need to read any of this out?
Yeah, pretty much all of it. I think that marker, like, when you get over it, I can't see the mark when you get over that.
Let me block the light. All right, so this is, can you see this part?
Mhm.
All right, so I just take that 1 right there, the upper, that goes first.
Right.
Really don't know if that can be seen any better. I block out that row and column, and then I have a 2 by 2
Right.
determinant of these numbers. And then minus negative 1 times, block out that row and column, I got negative 9, 0, 0, 4. Then plus 1, block out that row and column, and I'm left with those 4. Is that sufficient?
Mhm.
Okay. So this becomes 1 times 24 plus 1 times 36 plus 1 times 54. $114.
Wait a minute. Never mind. I see.
I'm not supposed to have made a mistake here, so I'm hoping the collective mind will see the mistakes.
So this is just the bottom piece, right?
Yeah, this is just the denominator of my fraction.
we're gonna do the same thing at the top.
Yes, we are. So we have 0 times, I really don't care, minus -1 times -4, 0, -8, -4. Plus 1 times -4, -6, -8, -6.
Can you explain again how you got to the top determinant?
Most of it is exactly like the bottom determinant. Except you need to bring this into account, this right here. And so that substitutes in for which variable you're doing. Since I have A listed first, and I'm solving for A here, I replace the first column. I replace the 1, -9, 0 with these 3 numbers here. So it's just substituting in for whichever one we're doing. When we solve for B, those will replace the middle in the numerator.
Okay, makes sense.
And so our numerator ends up being, so that's 1 times 16. Plus 1 times -4 minus times -6 is 24. Minus -8 times -6, which is 48. Which is no, -8. Because we have 16 minus 24. And so A is -8 over 114 amperes. Which I'm hoping is -0.0702. All right. All 3 techniques agree on what the value of our A is. All right, questions before I need to erase? Solving for B. My first column is the same as the denominator because I'm -9 and 0. B is the second variable over there in my list. I'm replacing that with 0, -4, -8. So my denominator is 114. And so I'm left with 1 times -4, 0, -8, -4, minus 0 times don't care, plus 1 times -9, -4, 0, -8. And that marker is losing its oomph. And so I'm left with 1 times -16 plus 1 times 72 56. So B is 56 1/14 amperes. I'm getting a completely different answer than
Why is it -16?
Positive 16. Thank you. That's where the mistake was. Please be one of those two. Which one?
Was that one,
This one?
Yeah, that one.
No, we made some careless error in the first technique. I did it. So the advantage of this is that we're not dependent, once we have the equations set up, as long as we set them up correctly, in some respects, there's less writing involved, and so less likely to make a mistake in that area. Obviously, it becomes more of a challenge getting negative sign. Well, actually, with all of them, a minus sign in the wrong spot completely changes everything. All right, so let's do it for C. See, first column will stay the same. Second column is the same as the denominator. Since C is the third variable here, we will replace that with 0, -4, and -8. And so -6, -4, -6, -8, minus -1 times -9, -4, 0, -8, plus 0 times 48 minus 24, plus 1 times 72. 96. Which presumably is 0.8421. Questions to hear? I'm going to do a shortcut for the 3x3 for those who have not dealt with it before.
I realize now that I actually just learned Cramer's rule.
Okay.
My differential equation, so
Okay.
I forgot the name of it.
In the linear algebra class, I think the book, somebody showed me a textbook a couple years ago from the linear algebra class where they actually do the proof of it, of why it works. And strangely, developmentally, I believe Cramer's rule was figured out before they figured out how to deal with matrices, which seems bizarre to me. All right, so let's just do a generic 3x3. A, B, C, D, E, F, G, H, I. Actually, I'm going to give myself some more room here, so let's erase some stuff. Perhaps get closer to the tile. Still sucking up. All right, so that's going to be A times what's left over, which is E, F, H, I, minus B times D, F, G, I, plus C, D, E, G, H. So this becomes A times EI minus HF, minus B times DI minus GF, plus C DH minus GE. Distributing AEI minus AHF minus BDI plus BGF plus CDH minus GEC. I'm going to get the positives together because of what I'm showing here. So I have AEI plus BGF plus CDH minus AHF plus BDI plus GEC. Double check, make sure I didn't leave something out, so good with positives. Okay. No careless errors to there. So that's not the shortcut. That I'm not asking you to memorize that. So what I have here is I have ABC, DEF, GHI. I'm just going to write the first two columns over again. So that's A, D, G, and B, E, H. So my positives, A times E times I. BFG, CDH. Those are my positives right there. The negatives, GEC, AHF, BDI. And then when you're comfortable enough with that, you don't even have to rewrite the first two columns. It's like going around the corner, AEI, BFG, and CDH are the positives, and the negatives go in the other direction, CEG, FHA, and IDB. Some of you probably can do that in your sleep, and some of you, if you're like most classes, aren't there yet. All right. Questions to hear? All right, so those are the three math techniques. We all started with the same 1 current per wire. There is another technique for setting up that some students prefer because you are dealing with basically 2 unknowns instead of 3 unknowns. But there is a confusion at the overlap spot that messes some students up. So I'm about to do the second physics technique called mesh analysis. I want to keep that. Let's get rid of that hard thing. And let's get rid of our currents here because that needs to change. Mesh analysis, or 1 current per loop. And and granted, there are 3 loops there, but we're going to pick currents for 2 of them. I personally prefer left and right as opposed to left and whole or right and whole, but that can be done also. So first thing, I got a loop over here in my left loop, and I'm just going to pick a direction for the current. It really doesn't matter which one I do, but this is for the whole loop here, and I should get a different color. See if this will show up. And I'm going to call this current A. Going clockwise in that loop. I'm going to do the left loop instead of the whole loop, because just for whatever reason, again, childhood scars. Let's go clockwise again, why not? Current B. And so now we do the voltage loops just like we did before. We pick a spot, we go around. I have 3 loops. I can do left, right, or whole. Or I could do, I need just 2 of them. I have 2 unknowns. So I'm going to start here. I'm going to do the left loop. So that's 1. This is my left loop. Minus 2A, because I'm going with this current A in the direction. Now I come down to the 6. I got 2 currents flowing across it. I have A and B. I'm going with A, so minus 6A, but I'm going against B, plus 6B. Then plus 3 minus 7A equals 0. The right loop. or hold, whichever one you like. I started here and went counterclockwise, so let's do that. So I have 5. I'm going across the 4, but I'm going against the current. I said the current's going to the right at the top here, and I'm going to the left of my loop, so plus 4B. Now I'm going across my 6 ohm resistor as I do my counterclockwise loop here. I'm going in the direction of A, against the direction of B, so minus 6A plus 6B plus 3 equals 0. So 2 equations, 2 unknowns. Let's simplify it first. I have 4. I probably should have picked something other than A and B, because A and B before represented the current in a wire, and this represents current in a loop. This A right here is not going to be this number. That B is not going to be that number, or that number right there. We will be able to get it from there, but, or actually, yeah, because A and B going the other way. A and B are not necessarily going to be those. So I have 4, and then my A's here. So 7, 13, 15, so minus 15A plus 6B equals 0. And then 8. Let's get rid of those. And then plus 10B minus 6A equals 0. And then you got, well, 3 that we've gone over. There's a slew of math techniques. It's 2 equations, 2 unknowns. You could graph it even and see where the lines cross. Matrices, that would work too. Let's do Cramer's rule. Why not? So I have negative 15A plus 6B equals 4. And then I have negative 6A plus 10B equals negative 8. And that should be negative 4 on top, not 4. And just to drill smaller numbers, this equation right here, I'm just going to divide by 2 to get rid of, to simplify it. Negative 3A plus 5B equals negative 4. And so A is going to be, my denominator will be negative 15, 6, negative 3, 5. Get these numbers right here. My numerator will be negative 4, 6, and 5. So I get negative 20 minus negative 24 divided by negative 75 minus negative 18, which is 4 over oh, there we go. I was worried we lost the negative sign. B, well, the denominator is negative 57. My numerator will be, I got negative 15, negative 3, and then negative 4, negative 4. So I get 60 minus 12 over negative 57, which is 48 over negative 57. And so A ends up being, I assume it is negative 0.0702. B, I'm going to assume is negative, did I have C in the, I think I had C in the middle before, or C on the right? I forget.
Yeah, C on the right.
Had C on the right, so B was in the middle. So it's going to be point, is that the 0.8421?
Yeah.
Negative So this gives us the numbers. We do have to do one thing at the end, though. The current going across, I had A going clockwise. It's a negative number, so it means it's going counterclockwise. So the current actually going across this and this would be opposite of A, and this would be 0.0702 amperes, 0.0702 amperes. Across here, I had the current in my setup was going to the right, but I got a negative over there, so it's really going to the left at 0.8421 amperes. And then in the middle, I have A going down and B going up. So in the middle, I have A going down, so negative 0.0702 going down, and negative 0.8421 going up. Or that's the same as 0.0702 going up and 0.8421 going down, which is a net result down of the difference between the two, which is 0.7719, I assume. And so current across here, 0.7719 amperes. And we got the same answer yet again. Wow. Questions? Oh, we already had test 1B right here, April 1st.
Was this chapter 28 or
Pardon?
was this chapter 28?
29.
29.
Yeah, that was chapter 29.
Or so we finished chapter 29.
Yeah, we finished 29. There's a reason I started out with the first test going through, in essence, this, because this section doesn't take as much time. All right. I will say test corrections by the end of the month. Again, you are trying to convince me that you understand. Two numbers at the top of the page, because I calculate your average two different ways, and then take the higher of the two, trying to determining the actual grade. This is all Daniel stuff. Oh, and before I flash anything here, let's go ahead and pause this.